Welcome back to the exam walkthrough. We're going to be doing 2024 Jan, question number 5, question number 13, and question number 15. These are all going to be from the electric field chapter. For the examiner report and the mark scheme, you can go to the end of the video. So I want you to try the question yourself, So let's start with question number 5. So it says a potential difference is applied across two parallel metal plates. Which of the following graphs shows how the electric field strength E varies with distance D? Okay, so we have some of the graphs, and the graph that most students get stuck in choosing between is either B, A, or even sometimes get stuck with D as well. Okay, so they get a bit confused with that. So basically what's happening here is we have, let's say, a charge. The charge that's here is moving from the positive plate to the negative plate. So it's moving like this. Yeah, that's clear. So as it's moving like this, right, it's covering distance, right? That's what that distance D there means. It means the distance that's covered by this charge that's moving. Okay, and we know that throughout this distance, the electric field will stay the same. The electric field strength will be the same. So hence the answer is A. Now students get confused with this distance as the distance between. There's a difference. There's a distance between the plates, and then there's a distance covered by this charge. Okay, which one are we talking about here? We are talking about the distance that's traveled by this charge, not the distance between the plates. If you change the distance between the plates, the electric field will change. But we're not talking about that distance. We're talking about, as I said a few times already, the distance covered by the charge. So I hope that point is clear, okay? That's why it's important to highlight this last point in the question. Which of the following graphs shows how the electric field strength E varies with distance D from the positive plate? So question number 13 says, in the early universe, a helium molecule formed when a proton joined with a helium atom. The helium atom in the helium molecule could lose both of its electrons in a collision. When this happened, the helium ion and the proton accelerated away from each other. And they've given us the initial separation from the helium ion and the proton. So we have to calculate the initial force between the helium ion and the proton. We can use F is equals to K Q1 Q2 over R square. And the charge of a proton is the same as the charge of an electron, which is 1.6 times 10 to the raised power of minus 19. I'm going to talk a little bit more about the charge on the helium ion. I'm also going to put the value of K there, and then the separation square. Okay. Now for the helium ion, we know helium is written like this, 4-2. Helium has 2 protons and 2 neutrons, and it has 2 electrons as well. So the electrons and the protons, they balance each other out, and then helium has no charge. But in the question, it tells us that the electrons, when they're gone, the helium atom becomes into helium ions. So right now, the helium ion has a charge that's equal to the charge of 2 protons. So I'm going to do 2 times 1.6 times 10 to the raised power of minus 19. Okay, that is the charge on the helium ion. Of course, neutrons have no charge. And then you have the charge on the proton, K separation square. Okay, so I've just plugged in all the values. Now let's get the answer. So the answer will be 7.4 times 10 to the raised power of minus 8 newtons. In part B, they tell us calculate the electric field strength due to the helium ion. So helium ion will be our source charge. Source. And then at the initial position of the proton. So that will be our test charge. Okay. So we have to tell at this distance from the helium ion, what is the electric field strength? So you can use the formula E is equals to K Q over R squared. Just plug in the values. Remember, this is the source charge. Source charge basically means the charge we're considering the electric field of. So we're considering the electric field of the helium ion. So we're going to get the answer as 4.6 m 10 to the raised power of 11 Newton per Coulomb. So question number 15 says, a beam of electrons was directed through a thin piece of graphite towards the fluorescent screen using the apparatus shown. A potential difference V was applied between the cathode and the anode to produce the beam of electrons. A diffraction pattern was produced on the fluorescent screen. From the diffraction pattern, the de Broglie wavelength of the electron beam was determined to be 2.55 times 10 to the raised power of minus 11 meters. And they want you to calculate the potential difference. So I want you to see here that the electron is going to move from the negative cathode to the positive anode. And it's going to gain kinetic energy and lose potential energy. Okay? And the reason it's gaining kinetic energy and losing potential energy, electric potential energy specifically, would be because of the work done due to the potential difference. That work done results in the gain in the kinetic energy. And work done due to the potential difference is equals to the voltage times the charge, or the potential difference times the charge. And that will be equals to the gain in the kinetic energy. Okay? So I hope this first formula is clear. Now, since we know that it's an electron that's moving, we can say that we know the charge. We know the mass of the electron, but we don't know the velocity. That's where the de Broglie wavelength helps us. So we can use the wavelength. We know the formula. Wavelength is equals to Planck's constant divided by the momentum. Okay, and then I can just find the value of the momentum. Now I've plugged in the values of the Planck's constant and the de Broglie wavelength to get the value of my momentum. So my momentum is equals to 2.60 times 10 to the raised power of minus 23 Newton second. Okay, so we can change the formula. So we know that VQ is equals to the kinetic energy. The work done by PD is equals to the kinetic energy. But kinetic energy formula isn't only half mv squared, it's also p squared by 2m. Okay, so now what we can do here is we can say the potential difference is equals to p squared over 2m cubed. And now all we do is just plug in the values. So I've plugged in all the values there. And now I'm going to find the value of the voltage. Again, the mass of the electron and the charge are in the data booklet. So we're going to get the value for the potential difference as 2320 volts. And then you can write it here as 2300 volts. So that's the value of the potential difference. Now I'm going to show you the mark scheme and the examiner report. I hope all the questions were clear, and that's all.